Wow, this bird is so cool. It's so cool that it's able to turn like that without a rudder. I don't know why planes can't do that.
Huh. Well, actually, a NASA scientist named Al Bowers just came up with a wing design similar to that. Basically, it's designed to turn without a vertical tail. He named it the Prandtl D wing, which also stands for the Preliminary Research Aerodynamic Design to Lower Drag.
It's not only an acronym, it's also a tribute to an accomplished scientist named Ludwig Prandtl. Prandtl was a scientist to come up with the term of stalling and research ways to reduce drag on aircrafts back in the early 20th century and was the basis of Bowers' research.
He was inspired by the way birds flew, and he designed it by making twist adjustments to the wing instead of a vertical tail rudder. Bowers was able to create wing vortices inboard of the wing tips as a result of the desired non-elliptical span load. Commanding a roll would be then created by creating more lift on the outboard of the wing vortices instead of on the inside. A rolling moment then banks the vehicle in the direction of the yaw, in its desired direction.
I mean, I just thought the bird was cool. Like, why does this really matter in the real world?
Well, theoretically, it reduces fuel consumption and allows the aircraft to perform more efficiently off of less fuel and reduces the weight of the wing.
Well, there is a clear implication that when applied to propulsion systems, a first-order analysis shows a 15.4% improvement in propulsion. System efficiency using this approach, there's also a 11% reduction in total aircraft drag due to span load. Elimination of the tail results in another 20 to 30% efficiency gain, and then 15.4% improvement in propulsive efficiency.
How does this relate to the adverse yaw of an aircraft?
I'm lost. What is that? What is that for y'all?
Well, if you want to come over here and look at this figure, I might be able to better demonstrate. So you see, if you look in the figure on the left, which is figure A, for an elliptic span load, which is also known as adverse yaw, this resultant force vector is not exactly perpendicular to the airflow. The larger component perpendicular to the relative wind is known as lift. For finite wings, there exists a component parallel to the relative wind. For elliptical span load, always in the direction with the wind, that is, towards the trailing edge. That is referred to as induced drag. Induced drag is the cost of producing lift with a finite wing. However, this design utilizes a principle known as proverse yaw, rather than the standard adverse yaw.
Wow, that's really interesting. What exactly is proverse yaw? I've never heard of it.
So now if you take a look at the figure on the right, figure B, the resultant force is angled such that instead of producing drag while flying, the airflow is angled into an upwash, otherwise known as negative induced drag, meaning that it is a more precise aircraft due to available upwash generated by the wing.
Alright, well, that's all pretty interesting.
Oh, it's similar to a bird's wing, so they also have an angle cord going directly through the wing, and they also produce upwash while gliding.
Well, if this design is so great, why isn't it used everywhere right now?
Well, because of the lighter design of the wing, you can't use ultralight materials because that would make it too light. Also, if it hits a crosswind or a very fast-moving gust, it would make the aircraft become unstable and hard to maneuver.
Well, yeah, there's that, but also you won't be able to use it for large commercial aircraft due to the weight limitations, and because large commercial aircraft need to store fuel in the wings, and this design requires a hollow wing with a cooler.
So where will I be able to see this implemented in the future, if anything?
Well, the design is more efficient and uses less fuel than standard aircraft design. Therefore, drones and small to mid-sized aircraft, especially commercial, will be able to take advantage of the 60% efficiency increase from the current modern wing design. Another plus is that since it has a reduced fuel load, it also reduces the carbon footprint compared to most modern aircraft, which is a huge issue right now.
Yeah, also, it's a lot more cost efficient because of the lesser weight of the wings and the reduced fuel used, enough so that NASA has started to experiment with how an aircraft with these wings would fare in an atmosphere similar to Mars. The hope behind a possible implication of these aircraft would be that they could replace the rovers and could cover more ground and be more elusive when faced with dangerous storms.
Wow, this is all really, really interesting. I'm excited to see what happens with it in the future.
Yep, 3, 2, 1, release. Give away all my secrets. There's the shoulder.